Assalamualaikum and good afternoon. Can you all hear me?
Waalaikumsalam warahmatullah. Yes, doctor, we can.
Okay, thank you. Okay, for this week, we are actually now in chapter 12, strength of the shear strength of soil. Okay, I already uploaded the teaching video in Facebook group. I hope you watch that video, and if you still don't do so, then you can start watching the video. Okay, in this topic, we are actually going to learn in briefly, going to learn how to calculate the shear strength or the shear at failure for a certain soil. Okay, to do that, we need to know the Morse column failure criteria, where we use the equation, this equation. This is quite, I would say, very useful equation. Shear at failure equal to C, which is cohesion, plus normal stress or sigma tangent phi value. Phi is the angle of internal friction. Okay, to use this one, especially in lab, what we're gonna actually, okay, the issue is like this. Let's say we want to build something, maybe a building, shopping complex, houses, or whatever engineering structure. We must make sure the soil is strong enough so that it can support the structure. That is very important. So in order to understand or to know that the soil is stronger than the load applied to it, or meaning higher than the load applied to it, then we need to conduct a lab test, which you are going to do, if I'm not mistaken, in the first week and the second week of June. So you still have a lot of time. So we conduct those tests, especially the shear strength test, consolidation test, triaxial test, and so on, many other tests, just to make sure that the soil can sustain the weight of the structure. That is the idea. So that the soil is not going to settle, meaning that move vertically too much. If the soil move vertically too much, then the structure will have problems. That we don't want. And that is why the reason we calculate or do the calculation for shear stress, or using the equation 12.2. So the idea is about the shear strength. Okay, actually that equation we can also find from the Morse column envelope or equation in the failure criterion for Morse column. So you get that equation too. So this is just a typical values of phi. Okay, phi is actually the angle when at failure envelope, or at failure, when the shear the shear stress at failure, and then we look at what is the angle or phi value for the soil. So this is a effective angle of friction for many types of soil. Okay, here the phi is here. Okay, normally when we conduct the test, I think later on I'll explain a little bit more about the direct shear test and triaxial test and also consolidation test. But in theory, in general, we have a failure plane when we apply normal stress. Normal stress you can imagine like a structure, but above the structure, the soil. So normal stress is contributed by the whatever above it, the soil above it, and also the structure. And there is also a shear when when there is a vertical normal stress here, vertical stress, and also the horizontal stress applied to the soil element here. So the soil will sooner or later will fail. So the failure line is shown by the AB here. So that is how, and what we are trying to find is actually the shear, this shear along the failure planes. And that shear is a function of normal stress and also the phi value. So when we conduct the test, is actually we have here normal stress in the x-axis, and we measure the shear stress in the y-axis, and then we plot what is the we shear this, for example, sample of soil until failure, meaning that the soil sample breaks or collapse. So this is at the maximum shear or shear at failure, for example. So in this case, we have like 4, but actually it's normally it's not like this, not like A, B, C here. Normally we take we run 4 times at least, so that we can get or plot this straight line, which in past the y-axis or shear stress, and the value is C or cohesion, and the angle of that plot line is the phi value for the soil. So this is what we are going to do, especially in direct shear test and also the triaxial test, just to find what is the maximum shear stress that the soil can handle. Okay, so in general, it is about that. Okay. Yeah, this one just show you the Morse circle and failure envelope where the sigma 3 and sigma 1. But actually, this is along this line, DH, this is actually the failure line. Here is a normal stress, and for the vertical or the axis Y, shear stress. So we're going to get a plot something like this one. But if we look at the Morse circle and the failure envelope is like this one. It is actually touching the line or the failure plane here. So D is the place where for a maximum shear stress at certain normal stress applied to it. So what is important here for you to know how to plot to get this graph, and then you will be able to find the value of phi, which is the angle here, and also the value of cohesion C, and able to plot the line. So that is the main task actually in this topic. Okay, the rest you can look, those are derivation and how to get the sigma 1, the equation for sigma 1 and sigma 3. Okay, for lab test, direct shear test. Okay, for direct shear test, here it is like this one. Okay, we take a sample of soil, put it in this apparatus, which is called direct shear test. Depends. Some sample we get from the site. Other sample, disturbed sample, sometimes definitely the disturbed sample. Some using the undisturbed sample, which is taken from the site without disturbing the sample, and some from the site, but the sample is already disturbed. We bring it to the lab and we can conduct the direct shear test. So here is actually we are forcing the sample to fail along this line, which is wrong actually. The concept is wrong. Actually, if we apply normal load here or force, and we apply shear, pushing, because there are two parts, upper parts and lower parts. Originally, it's just one part, but we can push the bottom part here, and the upper part still remain, and the sample will displace, and at the end it fail along this line, which is actually not a really good model, but simple model, because if we look at the soil, normally it will fail something like this one. This is the plane, not a straight line here. Not just a horizontal line, but actually there is an angle. There is the normal angle. Normally fail not at horizontal line. So it seems this direct shear test, we force the sample to fail along this horizontal line. But that is the easiest way how to do it, and the cheap way to get the shear stress and normal stress. But if we want to be more accurate, we can do a triaxial test. So this is a direct shear test, is suitable for sand, and mostly sand, but some also do for clay. But it's going to take longer time because they will slow the rate of displacement, and also to allow water dissipate or go out of the sample. So in order, that is what we call it consolidation. The sample must be consolidated for clay, and then we run the test, then we're going to get the effective stress. Okay, so normally we do it for sand, and it's very fast. The test. Okay. Okay, the apparatus is like this one. If you look at if you go to the lab, you will see the apparatus is like this one. Where here at the bottom here, we can apply loading. Okay. So we apply loading. And this load is actually giving the normal stress here. So the normal stress, we apply load here. So we need to calculate normally how many kilos time to get, we need to know the area here also, area of sample. And at the end, we can get the stress, which is applied to the sample normally, perpendicular to the horizontal plane. So vertical stress, that is given by this loading. And then since this sample, we need to shear so that we have a failure planes. So the machine here will push the bottom part here laterally, meaning that in horizontal direction, so that the sample is forced to fail at the end, until failure at a certain rate of displacement, for example 0.02 millimeter per minute or second, something like that. So yeah, this is the apparatus, and if we look here, this is the measurement for vertical displacement, and here we have the ring, load ring, so that we can measure the shear stress. Okay. Now this is from the top view. So this is the ring to make, because the machine will push the ring, and the ring will push the specimen here. So the ring here will be in compression. So the value will be recorded here. So we know the force or the shear stress or force, shear force from this reading. And this one is the reading for horizontal displacement of the sample. And this is for the vertical displacement of the sample. And if you look here, there is a hanger here. That this one is connected to the weight below the machine here. So normal stress is given by the hanger here. Okay, so that is roughly the setup for direct shear test. Okay, so at the end, if you run the test, will you see the shear displacement, horizontal displacement, and shear stress. So they are talking about this one. This is a shear stress. This is the shear displacement. So they record. When they push this one, this give value, and there is a displacement, and the sample is stressed until failure. And then they're going to get this graph. They can plot this one, shear displacement over shear stress. So they will get something like this one, the plot. For if it is a dense sand, so the plot is like this one. Loose sand, the plot, the typical plot will be like this one. So for dense sand, we can clearly see the peak shear strength. And for the loose sand, normally we just have ultimate shear strength. The peak is not clear, not so obvious. Okay, this one is in term change of height in specimen. This is vertical displacement. When for loose sand, when we apply load, it will just displace like this one. But for dense sand, first the sample will displace in compression, and then to a certain level, the change and the height, it is like pushing the sample now. So it goes to a different direction now. So that is for the dense sands. So from the behavior, we more or less know whether it is loose sand or dense sand. Okay. And this also show void ratio and sharing displacement. Void ratio, if you still remember chapter, I think 3, where we learn the weight volume relationship, where there is we give a meaning to what is the void ratio and so on. Yeah, for loose sand, it is like this one, and for dense sand, like the plot below here. Okay. So, and finally, we can plot normal stress over shear stress. And we're going to get this point here, there are 5 points, and then we can do line regression so that we can get, in this case, the C is 0, and there is an angle here that we need to find. So that is the phi value or angle of internal frictions. Okay. Yes. Sometimes we do the drain direct shear, and sometimes we just do the total stress direct shear. Okay. Okay. If you go over the example, you will understand how to do the lab test. It gives you the, for example, the result of lab, and then it'll show you how to calculate the stress and the shear stress and so on. And okay, for this one, sometimes we use direct shear test to know the interface here, the friction in the interface. For example, let's say we have a foundation here, like a foundation, and on top is a soil. So what is the friction between, or property between the concrete here and the soil? So we need to know what is the angle of friction. So of that one. So we can do the direct shear test also, just to get the value of this one, angle of friction between two different material. We can do the direct shear test for that purpose also. Okay. Okay, this is the same to show, soil. Okay, soil on top here, and here is the foundation, normally concrete. So we shear something like this one, so we get the friction angle for the interface. Okay, I think you can read the rest. Yeah, if you follow this one, you should be able how to calculate, how to calculate the shear stress at failure at the end. And you can also get the C, phi, and also the normally we look at for C and phi. Okay, for triaxial. Okay, for triaxial, now the apparatus is like this one. The sample is inside here, and we have like a container here, and then we apply load from the top here, axial load. This is actually sigma or normal stress applied to the sample here. Normally, the sample normally clay. We need to put in a plastic. There is like a special plastic which we wrap around the sample, and at the top we put the rubber ring, top and bottom, porous material, so that the water from the sample can move to the bottom here through porous stone. Okay, and there is some liquid here inside, and with the some pressure gauge, so that we can apply, if you still remember, sigma 3, the lowest, the minor principal stress. Sigma 3 is actually the all in the water inside pushing the sample with the value of sigma 3. So it's around, the pressure is all around the sample. And then axial load is actually sigma 3 without the sigma 3. Actually, so if you are talking about what is the normal stress applied, sigma 3 because it is the water also above, so sigma 3 plus additional stress due to axial load here. So that is the normal stress. So we can also drain the water inside the sample here. We can also let the water in the specimen or in the soil here run out or go out or drain. We can open and close the valve. So we can also, so there are many types of triaxial tests. Okay, there are CD test, consolidated drain test. There is also a CU test or consolidated undrained test, and a UU test, unconsolidated undrained. Okay, consolidated mean we need to make sure the sample here is consolidated, or meaning that the water from the sample is taking out, or the water drain only the soil inside. We need to, meaning that we have to compress the sample first until the water go out, all the water go out from the sample, only then we test it. So that is the consolidated and drain test. Sometimes if we were to do a consolidated undrained, meaning that the sample is consolidated, they apply pressure, but in that case they close the valve here, meaning that it cannot drain. The sample is consolidated, they apply pressure to the sample, but when testing it, they don't allow the water to seep out. First, they allow the water to go out because consolidation happen first. But in testing, they don't allow. So it becomes consolidated, meaning that the sample is consolidated, the water is going out of the sample, but they are doing the test, undrained test, meaning that the water is blocked, not to move anywhere when doing the test. And then the last one, unconsolidated, undrained. This is the most simple thing. You just take the sample and then run the test. You don't need to take time, consolidated the sample, and then you just close the valve here. Don't need to take time to make sure the water dissipate from the sample. So the quickest one is UU test, and then CU test, and the most difficult or taking longer time and more expensive is the CD test. So yeah, that is about triaxial test. Okay, actually I already explained quite a lot in the video. I try to make it simple. So there most important for triaxial for shear strength test is direct shear, because mostly the people outside or engineer outside, they ask for that result. And some, let's say the project is expensive, maybe they want to get a better design of the foundation, for example, then they request for a triaxial test result. So they need to get the sample and run the test. So it's taking time. And this is the triaxial unit. So this is a sample. This is a container, and here the load cell or the ring here will be pushed. Pressure will apply to the ring here, so the ring bend a little bit, so it gives the value recorded here. So we know the normal or axial stress. So the ring will push at the end to the sample here. That is axial stress. And then the sample is in a tube here and in a container which is filled with water. And there is a pressure that apply to the system here, so that we can have a sigma 3 here, minor principal stress inside the container, and sigma 1 by calculating the normal the sigma 3 inside plus the additional axial load. So we get the normal stress here. Okay, so the calculation depend on whether it is a UU test, a CD test, or a CU test. So you need to know, normally it's given, it tell you whether it's a consolidated drain. For example, here it mentioned, it say a consolidated drain. So this one is CD test. So CD test. So it will give you the parameters needed. So, and then for example, find the angle of friction and find the angle of failure plane, for example. Okay, so you can look at this example, and I believe you will understand it. Not difficult. Okay. And then, yeah, this is explained thorough about what is CU test. I think it's in my teaching video also. So you will learn better there. And this is when we apply the axial load and we have a confining pressure, which is sigma 3. So some sample going to fail, and the shape of the sample something like this. This is along CU test. Okay, at the end you're going to get this plot from the test. Okay, then we learn the UU triaxial test, and also the UC. This is UU. Okay, let me see. This is UU. So we have CD, CU, and UU for triaxial. And then there is another unconfined compression test. Here there is no water, there is no the sample is actually just put on a machine, and that machine will compress it. Not difficult, just something like this, the experiment for unconfined compression test. They just apply, make a sample and put it here, and they just apply the force, normal force, and until the sample fill. So this kind of test is good only for the soil, a clay soil. For sand, we cannot have the sample more or less like this one. So the sample must be able to stand on its own. We cannot have like pure sand where we cannot create a sample. So this unconfined compression test is good for clay material. As you can see here, normally the failure is like this one. This is the failure plane. When we apply a compression here, and the surrounding is not confined, the failure plane is like this one. So this one is more or less like a homogeneous material. Homogeneous material, for example, chalk that we use on the blackboard. The chalk, normally we can consider homogeneous because it behaves consistently at any location of the sample. So normally it gives you a 45-degree angle if there is a homogeneous material. For this is more or less about 45-degree. So this is, we can consider homogeneous material. Okay, and yeah, the rest anisotropy strength and vein shear test also. The test is like this one, and this is for very soft clay. It is like a liquid. Then we can use this one. If not, we cannot do the because it's going to use the tongs here. This one may break if the soil is too hard. Okay. This is just others experiment, other method. So you can look at my teaching video. Okay, yeah. And then we go to the summary. What is so the end of the chapter. So I already upload I think 3 questions from this chapter, and I hope you do it. And if you have any issue, you can let me know or discuss in this one, this meeting. Okay, is there any question regarding this topic, chapter 12? I open the question to the floor. Okay. Anybody?
Tak ada, Doktor.
Tak ada eh? Okay, so I think you need maybe some of you still haven't done because I just post the problems. So I'm thinking about because this course I'll try to make it easier for you and also for me. So we are going to have like 3 tests so that we don't have a big final exam. So 3 small tests, and then it become like we call it a continuous assessment. So for this, the first test, maybe I test you on chapter 10 and also chapter 12. Let me see. Okay. Okay, so actually we are actually now at week 5, and then and also the shear strength topic this week. So next week is supposed to be compaction. Some say you already learned compaction. Okay, but I think why don't for the first test 3 topic there: stress in soil mass, shear strength, and compaction. Is it okay like that? So chapter 10, 12, and 6.
Boleh, Doktor.
Is that okay? Okay.
Boleh,
Doktor.
Boleh. Okay. So when do you think you want to have the exam? I can upload the teaching video maybe after maybe today or tomorrow about the compaction. And then next week is supposed to be a compaction. Is it okay if next week this time we have a test 1?
Okay.
Okay. Okay, so next week we have a test 1. So compaction, we will discuss later. But since there is going to be a teaching video for you to look, and also I'm going to give you maybe a assignment for that. So you're supposed to finish it all before next week Monday. And Monday during 2, I would say 2:10 until 4, we will have the exam for test 1. Okay, I will also write and upload in the Facebook as well as the WhatsApp the time so that nobody will miss it. Okay, so that 3 chapter that we chapter soil and stress in soil mass, shear strength, and compaction for the test 1. Okay, if you don't have any question, we can just stop the meeting here. Is there any question?
No, Doktor.
Okay, no. Okay, if not, then we.
Doctor,
Okay, yeah.
For the compaction is chapter, which chapter? Chapter 6.
6, chapter 6, yeah.
Okay, thank you.
I heard from the last previous meeting, some say that you already learned it, but that's okay. Then since the material is also in this course, so we cover that one too. Okay. Any other questions?
Oh, sorry, doctor. And one more thing, I want to ask about the assignment. When we going to hand in the assignment? The assignment chapter
Okay.
10 and chapter 12.
Okay. Is it okay? After just submit after the exam, so that you can read. I don't know. Yeah, on Monday next week then.
Or next week, Monday.
Okay,
thank you.
Okay, I think I try to do the folder or whatever in the UKM folio. If not, I think so, yeah. So that you can submit. Okay, any other question? Okay, if not, then you may be dismissed. Okay, thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Okay,
Thank you, Doctor.
okay, Afwan.
Thank you, Doctor. Assalamualaikum.
Okay, salam.